Welcome, friends. I'm here another day. I'm still alive, and it's April 14th, Wednesday, 2021. And today, I'm going to bring to you something mind blowing. Well, not really mind blowing, but enough to get your brain cells working on this Wednesday evening. It's the middle of the week, so let's get going with some fast Vivaldi and some exciting leaf and tree problems. Alright, so if you like this video, like, subscribe, comment below, and don't forget to ask me any questions that you have, and let me know anything you want to do, any problems you want me to take on via algorithms, anything like that. So this problem tonight's a pretty easy one, as you can see on LeetCode. It's considered easy. It has 1131 likes, and it's got 47 dislikes. So it's, pretty well liked of a problem, probably because it demonstrates computer science fundamentals pretty well, and it's easy to throw together, I think. So the problem is, consider all the leaves of a binary tree from left to right order. The values of those leaves from a leaf sequence, okay, this is the tree, and the value of the leaves here form a leaf sequence 6, 7, 4, 9, 8. For example, the given tree blah 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 4, 6 to 8, as I just said. Two binary trees are considered leaf similar if their leaf value sequence is the same. So return true if and only if the two given trees with head nodes, root 1 and root 2, are leaf similar. So they could be completely different trees, right? Nothing is specified about the tree other than it's not a search tree or anything specific like that. It's just a binary tree with a leaf node sequence that's equal to another tree's leaf node sequence. And you can think about this problem. It's an interesting one. For example, often binary trees kind of give you decision. It's a decision space, right? Represents a decision space. So pretty much, if you have a sequence of decisions in your first tree represented by your first tree, and you have a sequence of decisions represented by your second tree, you can tell if your sequence of decisions kind of arrives at the same result using an algorithm like this, right? So it's a practical use case for anybody doubting the practicality of algorithms and data structures and knowing about them. It's very important. But anyway, let's continue. So how do we solve this? It's pretty simple. So we want to get the leaf nodes, right? We just want to check if the leaf nodes are similar. So this is what we would do. I'm going to keep my node lists similar. I'll call it leaves A, leaves A, leaves B, just to be clear. And pretty much I want to do a DFS, because in all of our tree problems, DFS is the most natural tree solving mechanism that we have initially, right? And we have a second root here, so we do two DFSs, and the end result is return A dot equals B. Leaves A, leaves B, and leaves A equals leaves leaves B. Okay, so there you go. That's it. Done, right? Well, no, we have to actually, obviously, write the actual algorithm out. So this is pretty straightforward, but there's something to consider. So our DFS looks like a standard def first search, where I'm passing my list of leaves. And I pretty much want to traverse this list. Root equals null. That's a recursive condition. So if we pass in a null value, we don't return anything. So we do DFS root.left leaves. Okay, now what I want to do this DFS, I want to do an in-order traversal. Why? Because I want to get the order of the leaves. I want to be consistent with the order of the leaves, right? So if in-order traversal maintains the ordering from left to right of all the elements in the array, right, in the tree. So basically, I want to maintain that ordering, and also because the ordering is important, right? The leaves nodes have to be in the same order. At the same time, I want to, so that's why, and it's an in-order traversal because I'm sandwiching my work between my primary work between the two recursive calls, the left and the right subtrees. So what do I do here? So all I do for my work step, root.left equals null, and root.right equals null. And then leaves that add root.val. And there you go. Should be as easy as that. Okay, let's run it. See what we do. Okay, it's true. And let's run. Yep, and there you go. Super fast. 100% of all Java submissions, though I imagine because all other Java submissions probably have a similar result. And the memory usage is better than 90.81% of Java solutions. I really can't imagine there being very much of a way to optimize the memory by that much, perhaps using a different storage data structure for your array list, but this is pretty good in practice. So, yep, that's it. And yeah, that's a short problem for tonight. Just wanted to record something. Remember, like, subscribe, and let me know if in the comments below if you like my videos. And I will see you later. Have a good night.